Okay guys, we can deal with feed rates now, and this is really easy stuff. It's not half as complicated as a lot of the books and equations that you can see written out make it look. So I've done this in layman's terms just to make it easy, more easy for people who aren't used to doing it. So the first two things to note: if you're in a home shop like I am, unless you've got a power feed on any of your axes, then feed rates you can almost ignore it, because there's not really any way of calculating what you're running at. If you're in a home shop like I am and you've got a lathe a little bit similar to mine, there's probably more chance that you're going to be able to do it, because if you've got a gearbox in the headstock and a traverse for the saddle, you'll be able to program the traverse to travel at a certain rate. So turning, you can potentially do it in a home shop. As I said, milling, unless you've got power feed, then you're going to struggle with this, but even so we'll go through the calculations and I'll show you how I do it, and I think this is a much more simple way of doing it than some of the books would lead you down. So again, in terms of nomenclature, FPT, which is feet per tooth, and that can be in millimetres or inch, or FPR, which is feet per revolution. So if this is a milling cutter, it's 1 revolution of the cutter, and that can be in millimetres or inch per revolution. So I've done a worked example and I've used the same data as before, and again I've just taken it straight out of the Presto book that we used earlier on. So this is for 60 Newton metre steel, so sort of a low to medium carbon steel, using a 1/2 inch cutter again. 600 was the sort of surface speed calculation that we got to the revs a minute earlier on. It was closest to 600, I think, so we're going to use that same example. So the way I do this, and the numbers out of the book, is 4 inches a minute feed rate for that cutter in that steel, which is 101 millimetres per minute in metric. So the way I do it, I've assumed this is an end mill, it's a 4-flute cutter, so if you think about it, in a minute, in 600 revolutions of the cutter in 1 minute, if you times that by 4, you get to 2400. That's how many teeth are going to pass the work in that minute. So the 2400 times the tooth is going to pass. So if you look at your metric calculation, if you take your 101, divide it by 2400, that's going to get you to 0.04 millimetres per tooth. So that's your FPT, feet per tooth, in millimetres a minute. For metric, do the same calculation for imperial. So this time I've taken, it's 4 inches a minute. If I times that by 1000 for thousandths of an inch, that gives me 4000. Divide that by the same 2400 number, which is my revolutions, and I get 1006 per tooth. So it's dead easy to work out that way. If you just think what's going on with the tool revolving, you'll see lots of calculations where they'll start drawing formulas where you cross minutes out and divide it. It works, it's the proper mathematical way of doing it. This is the layman's way of doing it. I always think about what's actually happening. I visualise the cutter spinning, visualise the distance it's going to travel in a minute, or if it's a lathe, the part spinning in the chuck, and how fast my tool is going to approach past the workpiece. The consideration for turning, so we've calculated feed per rev. We've calculated feed per tooth. If you've got 4 teeth, you times that number by 4 and that will be your feed per revolution. Turning, it's normally expressed in feed per revolution, and again it can be in millimetres or inch per rev. The only consideration that's worth noting, and this is something that people often miss when they're turning in a home shop, is that for the Z-axis, which is the saddle, you've got a ratio of 1:1. So if your gearbox tells you you're travelling at 0.2 of a millimetres per rev, that's what you'll actually be travelling at. Don't forget, if you're travelling in the X-axis, because you've got the whole diameter versus radius thing, you've got a 2:1 ratio. So at that point you should halve your value. So if you're looking to travel at 0.2 per rev, you actually need to be programming your gearbox at 0.1 per rev, because you're taking twice the amount of material because you're working on a diameter. And that often gets missed on manual turning. Alright guys, in all the calculations we've just done, there's one of the variables that we've not really spoken about. So we've spoken about diameter and various other bits and pieces, cutting speeds, N being RPM, S being speed, cutting speed. And there's one that we've not spoken about, which we're going to go through now, and the clues are on the board behind me, and you might have guessed it, it's pi. So, and the astute amongst you will probably notice that I'm filming this out of sequence after a small accident with a tin of soup and my nice light coloured sweater that I had on. So we're just doing this a little bit out of sequence. So what about pi? And again, it's a constant value, and I spoke about that before, but it's a relationship of pi to the diameter that you're talking about that's really, really important, and that's why turning is significantly different to milling, whereby with a turning tool, as I said before, your diameter is always constantly changing, and that's why when you multiply that by pi, you're getting a different result. Your maths will be different all the way through. So I'm going to come to the table a minute and just go through a representative example just to show something that most of you who do this kind of stuff and who've got workshops and have played around with tooling will have been familiar with at some point or other in your time doing this. And I'm going to explain why pi is the reason for the issue that you'll have all had. So we'll just bring you back in at the table and we'll go through that now. So, two examples, a spot drill and a centre drill, and I've picked big ones so that it shows up on the camera a bit better, but they're representative pretty much in diameter, in diameter sizes, so they're representative examples of a centre drill and a spot drill regardless of the diameters that you happen to choose. So if you think back to the pi calculations that we've done, pi is always used with D and diameter in all of the calculations that we do. And when you actually look, I'll just find a pointer, when you actually look at the point of a centre drill, and we'll just bring that into the camera, the really important thing to note, and this is the same for a drill or any other tool that's centre cutting, right at this very point at the middle, right at the very, very centre, your D value is 0. And if you multiply anything by 0, your end result is 0. So your cutting speed at the very centre of that tool is 0. Regardless of how fast your spindle's going, you could be doing 30,000 RPM and your cutting speed at that very centre point there is still 0. And if you look at the thickness of the web on that centre drill, and then you compare that to the thickness of the web on the spot drill, representative size spot drill, you will probably now understand why you break a lot of these things, because you're forcing quite a thick section into some material with 0 cutting speed in that centre point. And then what happens, and anybody who's drilled manually will know this, and we'll take the spot drill as a drill in this instance, as you start drilling in any material, it's normally quite tough going when you first plunge the point in, and then as you gradually get in deeper and deeper into the material, you'll find that the drill wants to cut more and more easily into the material, and that's because your cutting speed is increasing as you get deeper and deeper into the diameter. So that's why really these are the best option for starting any hole off, and I'm going to go into that's the proper way to do it in another video when we talk about cutting tool geometries. But I just wanted to use those two as a good example of cutting speed being 0 right at that very centre point, and that's why the thinner that web is at that centre point, the less stress you're putting into the tool and into the workpiece at that particular point. And if you put less stress into the tool, you're less likely to break it, and that's why so many of these break off when they're being used. So I thought that was interesting, useful to consider, and a good example of how that pi and diameter relationship work together. So we'll just move back up to the whiteboard, one more example of pi, and then we'll get back to the rest of the video with the other sweater on. Okay, so here's a pi example that when such things as pubs open back up again and life gets back to normal, will be a good pub talking piece, or if you're with friends or whatever. Something that I heard about many years ago, and I've never forgotten it, and it's a really good example of the relationship between pi and diameter. So it's about the best circle I'm going to draw. That's our Earth, and I'm going to do a lot of rounding here just to make the maths easier. So 8,000 miles d. So the diameter of the Earth, 8,000 miles. So if we times pi by d, we get the circumference, and that's the formula that we've been using in the previous examples with the cutting tools. So pi times d, and again I've already done this off camera, I know what the answer is roughly, and I'm going to round either up or down, I can't remember. But effectively the circumference, so the distance all the way around the Earth, so we'll call that c for now, is 25,000 miles. So here's the thing, if you took a piece of rope and you started at one particular point on the Earth and you wrapped the piece of rope all the way around the Earth and laid it on the surface, you would need a piece of rope 25,000 miles long to get the ends to touch, assuming you were on the equator. So, and I know somebody's probably going to say it's different at the poles to the equator, but you know what I mean. So here's the thing, if I was to then build a series of posts that were all 1 foot high, and I'm obviously going to need far more posts than I'm going to draw here, but you get the idea. So I stick a load of posts in the ground at 1 foot high all the way around the Earth. Try and speed this up a bit, something like that, and I get my new piece of rope, which will need to be longer of course, and I put my new piece of rope on the top of those posts all the way around. Question is, how much longer does that piece of rope need to be to stand 1 foot off the Earth's surface all the way around? And this is the bit that's really surprising. Any answers? It's a shame this isn't live, because I love the answers to this question, you get all sorts. The actual answer is 6.3 feet. And that's the really interesting part. So you think of the distance we're talking, 25,000 miles of rope, we stand it 1 foot off the surface, and it only needs to be 6.3 feet longer. And that is that relationship between pi and a radius, or the diameter in this case. So 1 foot one side and 1 foot the other side is 2 feet on diameter. 2 times pi, which is 3.142, is pretty much 6.3, and because the unit is feet, the extra that we've added on is in feet, 6.3 feet. So that just shows it's a really strange relationship between pi and diameter, and we've just looked at that on the spot drill and centre drill. So I'll bring you back when we move on to the next piece of the video. So one quick last thing I wanted to touch, and we're back to equations again, and apologies for that. I know it puts some people off, but I'm going to try and break some of the myths behind equations. So this is the one we looked at earlier. This could quite easily say 12s over pi d if we were working in imperial, as we looked at earlier, but we'll use the metric one for now. You may say, but I already know n, I know what my RPM is, I don't have a book or anything, but I actually want to know what my S value is. So I know what my cutter size is, I know what pi is, I know what n is because I've just chucked a tool in my spindle and I know I'm running at 1200 RPM. What does that make? What does that make S? So basically, you'll rearrange the equation, and a mathematician or anybody who's doing this will just go S equals, rearrange it, dead simple. Lots of people, and I used to struggle massively with maths. I was rubbish at it at school, completely rubbish. And I only sort of got to grips with it in my late 20s when I went back to college and actually applied myself and tried to understand it. And I got to the point where I could do this stuff fairly simply, you know, even with much more complex equations. But in the time that's elapsed since then, I have to think quite hard again about how to do stuff like this. And I always go back to the kind of layman's way that I learned this. So basically the easiest way to do this is to just isolate S, because it's S that we want. It's S that we want, and we know that N equals all of this lot. So conversely, all of this lot equals N. So it doesn't matter whether you're reading from left to right or from right to left. And I know all the mathematicians will be frowning at me now, but I like to read, if I'm transposing this to understand what S is, I like to read from right to left because it makes it much easier to visualise. So we want to keep S on its own, and the very simple rule about this is if you're moving anything from the right hand side or the left hand side of the equal sign to the opposite side of the equal sign, if it's on the bottom of the equation it goes up to the top, and if it's on the top of the equation it comes down to the bottom. That's all you need to remember. And then basically you take one thing at a time and move it over to the right place on the other side of the equal sign. So we'll leave it all up there for now. So we'll draw our centre line in. We're going to move the 1000 across, so we'll put that down here, but it's going to the bottom of the equation. We're going to get rid of pi and d, so they're going past the equal sign, which means they're going up to the top. So pi and d up there, which means we can now get rid of all of that apart from RS, which we leave on its own. We don't do anything with the n because we've not moved it. It's the same side of the equal sign as it was at the start of this. So we've now got S equals n times d times pi divided by 1000, and that will give you your S value. And if you want to make it look right at that point, all you need to do is, and I've run out of space, but you would basically get rid of your S and write it at the front. S equals pi dn divided by 1000. Simple as that. And you can rearrange that equation for any one of those things in that very, very simple way of doing it. And just by moving it all back to the left, it's just, I found that really easy, and that's how I got my head round it and started to understand it. And a lot of the maths lecturers would never do that, and they'd just rewrite it, and you sat there scratching your head trying to work out, especially with really complex ones, how they've just done that in their head. But for me, I like the visual, and moving right to left, just transplanting it, getting rid of the bits you've moved. Dead easy, dead simple. And I'm just hoping that there may be some of you out there that haven't done this for many, many years, and that's hopefully busted some myths around it being a complex thing to do. It's not, it's really, really easy. And I think that's, without this episode going on too long, I think I'm probably going to call it at that. I've gone through the rudimentary basics of it, simple calculations, some experiences, some considerations. So I'll just wipe the board again and we'll do a final sort of tips. And I'm going to wrap each one of these episodes up with a bit of a story, hopefully a funny one, if I can make it funny, of an experience that I've had in my lifetime. That relates in some way to this, and it might be quite loose, but I'll try and pick something that's happened that's a bit of a funny story. So I'll just clean that down and we'll come and finish this one off. Okay guys, so we'll just summarise what we've been through there. So use the book data, the website data, the supplier data as a guide only. Don't get too bent out of shape trying to get to the exact numbers. It is a guide. Keep your setups as rigid as possible. So we've already been through that and the importance of that. Keep tool stand out as short as possible. Run out of room on the board there. Most importantly, really, of all things for successful machining, those are two of the key things. So if you're not doing those two things, you're going to struggle with everything else. Know your machine and its limits, and the only way you're going to have got to that point is to have pushed the limits safely. So always do it safely. Make sure you've got the correct glasses, safety equipment on when you're doing stuff like that. Try out finished cuts in roughing stock. So again, same material, same setup, we've already spoken about it. Use that rough stock to understand your setup and everything else. Consider all the variables, and coincident with that is minimise the number of interfaces, and that could be in your spindle, it can be in your vise, in your table, in your setup, in your chuck, in your tool post on your machine, if it's a lathe. Every interface is a weak point, and a combination of all of those interfaces, every time you add one, you reduce your rigidity. So, and what I've said there is factor down accordingly your speeds and feeds depending on the amount of interfaces you've got. So count your interfaces up. If you've only got 1, 2 or 3, you're going to be fairly rigid. If you've got 7, 8, 9, 10 different interfaces, then be prepared to factor your speeds and feeds down as a result of that. Use coolant if possible. I always suggest, even when I'm running tools where like carbide cutters in my milling machine, I can only run at 1600 RPM flat out. The carbide tools I'm using, 10, 12 millimeters, will do 4 or 5 times that in steel, no problem at all. But I still use coolant, and it's just about prolonging the life of the tool really. Carbide tools are expensive. You want to try and get the most value out of them. Start low and work upwards. So again, going back to your book data, start at the low end, and if everything's going well and you're cutting well, then you can sort of step it up and see where you get to. Don't forget to try a faster RPM. Now, we've not covered this yet. Really important. Typically what you'll do, you'll start cutting something. If you get vibration, there's a tendency to say, I'm going to slow it down. I'll slow it down a bit more. I'll slow it down a bit more. And I've done that on my mill. I was using, I think it was a 14mm, what was it? No, it's bigger than that, 20mm solid carbide end mill. And I was just getting vibration, slowed it down, still getting vibration but a different frequency, slowed it down again, still getting vibration. And I just suddenly thought, it's carbide, it will take the speed, I'm going to put it up to the full 1600 RPM. Tried that, straight through, all the vibration disappeared. So that's all about harmonics and vibration, and we'll probably cover that in a separate workshop tips video. Remove swarf regularly. Swarf will interrupt your cut. If you've got a slot that's full of swarf and you're trying to machine into it, you'll hear it crunching and grinding. It's no good for your tools, it's no good for your part. It's no good for the stability and rigidity of your setup, so keep areas clear of swarf. And most importantly, have fun and enjoy the learning experience, and don't be afraid to break tools, because it's only by breaking tools, pulling your machine up, all of that stuff that we've already spoken about, do you start to understand your machine properly, and then you can start to make good assessments nice and early next time when you start to hear and feel the same kind of noises, smells, all that stuff that we spoke around senses. It's only by getting it wrong and learning from that, and it's often good to note down what you were doing. So when you've had a tool break, make a note of it, what speed you were running at, what metal you were cutting, what the conditions were, so that you can start to build up knowledge that way. So that's kind of the summary. So what we'll do now, I'm just going to go to a bit of a funny story, and this goes back to my apprenticeship, and it's kind of loosely related to the keeping setups as rigid as possible and keeping tools stand out to the shortest possible, even though it has nothing to do with machining. So in my apprenticeship, when I very first started, I was on an EITB training course, and there were second and third year students in the class as well as first year students, and I was in the first year. And a couple of the second and third year students who've been around the block a few times and were starting to get a little bit cocky, they used to like picking on the first year students a little bit, and some were quite savvy and kind of knew what was coming, and others were a little bit green, shall we say. And there's this one poor lad, and I won't mention his name just in case he's ever watching this, but he'd come fresh out of school, obviously never picked a tool up in his life, was learning from scratch, and bless him, he got picked on a little bit, and he was busy trying to cut some sheet steel in a vise with one of these, and he'd got the sheet steel basically stuck out the top of the vise, I don't know, a good 6 inches if not more, and it was sort of 2mm plate, and he was here busy trying to hacksaw it, and it was squealing and screeching and making a racket as it would. And again, it goes back to that keeping everything tight, rigid to your clamped area, same deal. And so the apprentice master was actually not in the shop at the time, and we obviously heard him struggling with this, and a couple of the older lads went up to him and told him to stop and said, you're using the wrong saw, you need to use a raw saw. And he said, what's a raw saw? And they said, we'll go and fetch you one. And they came back with a set of these, which are thread pitch gauges, and basically told the guy what you need to do. I know they look really short, but they do work. So what you need to do is work your way through, you know, start at the coarsest teeth, and then gradually keep working through until you find the sort of set of teeth that works for you without the noise. So he's busy away, he's busy away taking all the teeth off the apprentice master's best set of thread pitch gauges, just as the apprentice master walked back in the shop to see him doing it, and he clipped him round the ears and gave him a row for wrecking his best set of thread pitch gauges. And of course the guys that had told him to do that were nowhere to be seen at that point when he turned around to point to say, so and so told me to do this. There was absolutely nobody there to point at. So I'll never forget that, and seeing the poor guy trying to saw 2mm steel plate with a set of these was just something funny. It shouldn't, you know, it wouldn't happen these days in an apprentice shop. The world's moved on, we're in a different place, but back in those days that was run of the mill, as was going to fetch a bucket of steam and a long wait and various other things that apprentices used to get their run around with. So I hope that was interesting. Obviously, if you're a competent machinist, a lot of what I've just been through there you probably already know. If you're not, then I hope some of that was useful. I've tried to use layman's terms, I've tried to let you benefit from my experience, and what I'll probably do in future ones of these, and it's been difficult to do that today because my milling machine's just out of action at the minute, but is set some practical examples up to demonstrate the theory that we go through. So that's what I'll be doing in future ones, so it's not just all talking. What I'm probably also going to do is have a think about what sort of topics to cover, and I'm thinking about vibration being one, and frequency and getting rid of vibration, that kind of thing. Maybe thinking around accuracy of machining and how to improve your chances of getting things right, and that will probably include, and I've covered this once or twice already, but on the lathe doing balance cuts to get to a finished diameter, and we'll probably do a bit more on that kind of thing, and various other topics like that, just pulling from the kind of experiences that I've had. So I'll have a think about what sort of things to go through, but if anybody has got something that you think you'd like me to try and cover, if it's within my field of experience and knowledge, then by all means I'll stick that in as a tips video for the future. So I hope that's been something a bit different. I hope it's not been too sort of tedious just with the talking and the sort of lecturing and pointing at the whiteboard. Hope you found it useful, and we'll catch you all again very soon when we'll be making some swarf, and I'm going to get back onto machining and probably back onto projects, making some more tooling for the shop. So we'll catch you all very shortly.